Yes.
The camera is this one, so people just seeing you from this camera, you want to talk maybe to people, and this is what they see. If you change, they see the slides or they see what you write. Students online courses, but normally is on time. You give online.
Online.
You give online courses normally? You are used to, or is on site?
No problem. Yes.
Of course, Alexandre, yeah. In 5 minutes. Because we wrote in at 2 p.m. and you start. You can give 1 2 minutes to people, so about 2 and 2 you can start. Because normally people have to access and they have to register, so it takes maybe 1 2 minutes. You can send the chat. You have 8 people now. I see.
Can begin. Hello, everybody. I am Alexandre FOTUE TABUE Alexandre, lecturer at University of Bertoua, Cameroon. Welcome to this short course of finite rings and their applications in coded theory. Course is composed of 4 lectures. In 4 lectures, we will explore how algebraic structure and more specific finite ring can be used to construct error correction codes. Lecture 1 will cover the basic of finite field and laid the foundation for more general ring structure. In lecture 2, we introduce a finite local ring and concept of coefficient ring, especially for understanding code over finite local rings. Third, lecture 3, focus on Frobenius ring, essential for preserving MacWilliams identities in coded theory. Last lecture explored the theory on coding over rings, from code over Z4 to general construction use channel ring with computation. Example use SageMate. Our goal is to combine theory and computation to provide you with both a deep understanding and practical tool. Thank you for your participation and hope you find this adventure existing and regarding. Lecture 1, finite field. Finite field is algebra structure used in code tutoring for constructing a correcting and error correcting code. For example, QR code use a Ring-Salomon code over finite field of order 2 power A. In cryptography and combinatorics, finite field are important tools. Objective of this lecture, firstly, we construct primitive polynomial over finite field of order Q. Second, you perform addition and multiplication operation in any arbitrary finite ring. Finally, we factorize x power n minus 1 in polynomial rings over finite field Q for any prima power Q and any positive integer n. You start to give the background on ring. What is the ring? The ring is the triple R plus R is a non-empty set. First law plus is additive and second law is multiplicative. Commutative ring with identity is first R and first law is an abelian group with additive identities denoted by 0R. Second part, we have R and second law is a commutative monoid with multiplicative identities. We denote this by 1 power R. Third, a second law dot is distributive with respect to plus. We have this picture, first member from first member to second member, we expand second member to first member to factories. This descriptive law establishes a relationship between first law, that is the first law plus and second law multiplicative. Of course, the ring with identity if 0 different to 1. We have a specially element in the ring. Special element, you have a place, you have a relation between two elements in the ring. This relation given by divisibility. We say that D is a divisor of X, or D divides X if D is different of 0 and X is multiple of D. We denote DRX, the set of divisor of R. A unit is the divisor of 1, and 0 divisor is a divisor of 0. Sure, the set of divisor of 0 and group of unity has the intersection between two sets is empty. We say that D is irreducible in the ring if D is not a 0, D is not inverse, this is not a unit, and D is a multiple, and divisor of this is the lambda D, where lambda is a unity. We have two rings. First, integral domain. Integral domain, ring is an integral domain if it has not divisor of 0. And ring is the field if any non-zero element is a unit. For example, we have set of integer with natural addition, natural multiplication, and a natural multiplication of the algebra structure is the ring. When we define the set Zn by 0, 1, dash, 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 n minus 1, we define two new operations, plus or plus and or die or dot. The addition the addition perform modulo n and multiplication perform modulo n. This algebra structure is called ring of integer modulo n. For example, in Z, the prime number are irreducible, and Z6, we have 2, 3, 4 divisor of 0, 1 and 5 and a unit. In Z8, the divisor of 0 are 2, 4, 6, because 2 times 4 equal 8, modulo 8 is 0. And unit in Z8 are 1, 3, 5, 7. Now we have we have a algebra structure definite a ring. A second, you have the special set in the ring. Special set in the ring are ingel. What is ingel? Ingel is the subgroup. Is the subgroup of ring. Verify following property. If we take element of the ring R, an element of the set I, the products in leave the product in a set I. Angel is the principle if we can put in the form A, where A is a generator of angel. Angel is the maximal if has not content. It has not it has not if I place angel is the maximal if any angel G of place.
This one, I think. Yeah.
Okay, I continues. We continues. Please explain. Okay, in E are maximal if E implies space. E is maximal in the ring A if E content G place if E strictement implies J equal R. E is maximal in R if E strictement is if J contains strictly E imply J is equal R. Okay, continues. Ingest I and J in a coprang I plus J equal E ring. We have special ring. Ring is the local if has only maximal ingest. Ring is a principal ingest ring if all these ingests are principal. A ring is a principal ingest domain if it's an integral principal ingest ring. Ring is a unified factorization domain if it's an integral ring where every non-zero and non-unit element factors uniquely into irreducibles up to order and unit multiple. For example, Z plus dot and polynomial ring over field are unit factorization domain, where for all integers n greater than 2, Z, the ring of integers modulo n is not domain principal integer ring. Finally, where for any integer n greater than 2 and any prime p, Z p power n is local ring. We know that you note that the local, this special local ring, cardinality is the power of the prima. We are return this in the following. Let R be a final, the final commutative ring. We have this result. Any principal agent domain are unique factorized ring, but inverse this is not true. This exercise give example an integral domain is not unique factorized ring for any field. When R is a principal integer domain, the sum of two integers is generated by GCD of generator. An intersection of two principal integers is generated by least common multiple of the generator. Carve out of this code, unless otherwise specified, the notation R is a ring. We make that R is commutative ring with identity. When we say ring, we say it's commutative ring with identity. Ring is the local if we has unique maximum. The following assertion is equivalent. We characterize local ring for ring assertion. R is the local ring if and only if R minus unit group is an integer. Et this integer equal maximal ring. Third, R is the local ring if and only if the only idempotent element are 0 or 1. Finally, R is the local ring if and only if all elements in integer is maximal integer. We have 1 minus A is a unit of the ring. Definitions. A characteristic of the ring. A characteristic is the ring is the non-negative integers verifies Zn can see us of the subring of R. Explain that. Explain that we take okay. A characteristic of the ring is a characteristic of the ring. We can define as the additive order of 1. We take 1 plus 1 plus dash 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 plus. When is a 0, the small the small the most less non-negative integers verify 1 plus 1 plus 1 equals 0 of R. We call it the characteristic of R. For sample, a characteristic N is characteristic for R if there exists a monomorphism of ring monomorphism to Z and to R. That of K element of R associate K dot 1R. Donc, N is the characteristic of R if ring of integer modulo N can be injected in, can be can be C of the subgroup of the subring of the ring R. Okay. For position, we have important example. We have important result. If R is the local, his characteristic or 0 or characteristic is the power of the prima. For example, the field characteristic of the field is 0 or a prima. A field is the example of the local ring. Singleton 0 is the maximal integer of the field. R is the field if R is the ring if its maximal integer is singleton 0. Generally, characteristics of the local ring is 0 of power of the prima. Okay. We have you need in the circle of the concept multiplicative order. The multiplicative order of the x is the unit in the ring. The condition F is a unit of the ring. The characteristic of x denoted by ORX, defined by 3. Characteristic also is the smallest positive integer such that the s power of k equal 1. For example, in the ring of integer modulo 7, order of 2 is 3 because we have 2 power 1 equal 2, 2 power 2 equal 4, 2 power 3 equal 8, modulo 7 equal 1, and so on. We compute the characteristics of 3, of 4, of 5. We know that the characteristic of 3 equals 6. 6 equal 7 minus 1. 6 is the order of unit group of the ring. We know that the multiplicative group or unit group of the ring 7 is cycled, and its generators are 3 and 6. That example we find in these questions. What find on the question, does do any ring in you is unit group of integers in the ring is the unit group of the ring of integer modulo prima p is a cyclid. Answer is yes. Theorem give the answer if P is the prima, the subgroup of the ring, the subgroup, place if P is the prima, the group of unit of the ring of integer modulo P is the prima, is the second. To prove that is enough to show that there is existence of element of the group that the order is the P minus 1. How to find a generator of this group? We have this algorithm. We factorize P minus 1 into prima factors. Second, I pick up D between 2 and P minus 1. I compute G power P minus 1 over Qi. When power is different to 1 modulo P, for all prima Qi, we take G as a generator. Otherwise, and return the first such as G found. For example, we pick up P equals 7 and factorize 7 minus 1, we obtain 2 times 3. We take G equal to, we have 2 power 6 over 2 equal 2 power 3 equal 8 modulo 7 equal 1. In Koji, in algorithm, 2 is not a generator, and delete 2 and take 3. 3 satisfies the condition of the algorithm. We take 3 as a generator of this circle group. Primitive element. What is the primitive element? The primitive element is the generator of the circle group ZP. The generator of this group I call it the primitive element. We take F, a finite field is the ring whose non-zero element is a unit. Let F be a finite field having a q element of characteristic P. E and field extension of F. We can view F as a vector space over Fp. Fp is the ZP. P is the characteristic of F. You recall that characteristic of the field is 0 or prima P. When F is finite, the characteristic of F is the prima number. Second, F is the expansive field of the polynomial x power q minus x, where Fij is the algebraic closure. Algebraic closure of the polynomial is the field where this polynomial factorizes into polynomial of degree 1. Important result. The group of units of the finite field are cyclic. The element of the unit group of this unit group are called primitive element. Other functions allow us to compute the number of primitive elements in the finite field. For example, the finite field of order 7 has 6 for example, how many primitive elements are there in finite field order 7? The number is phi7. Okay. Please. Okay. This finite field has two primitive element. And then these primitive elements are 3 and 6. Okay. First questions, how to construct a primitive element of the field F. F be a finite field of order Q. Small f is the monic irreducible polynomial over field of degree T. Then principal integer generated by F is maximal integers of the ring of the polynomial ring over finite field F. Hence, field, the Gaussian ring F, the Gaussian ring E is also a field because integer generated by F is maximal. Besides, field E can be viewed as the vector space over F whose D tuple 1 alpha dash 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 alpha power D minus 1 is the basic, where alpha equal x plus integer generated by F. So that we have we see that E cardinals E is a Q power D, where D is the dimension of E over F. F divides oh, okay, explain that. We take F cardinality Q, E a Gaussian ring Fx by principal integer ring generated by F. Alpha is x plus, we have F of alpha is the 0. E is a finite field. It's the finite field with order Q power D. D is the degree of F. E can be viewed as a vector space over F with basic 1 alpha dash 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 alpha power D minus 1. Okay, we can see that to construct a field, we have a ground field F you need a ground field F and a polynomial and a monic irreducible polynomial to you repeat to construct the final field. You need the final field F and a monic irreducible polynomial over this final field of degree T. How to determine this monic irreducible polynomial over final field F? That is our questions. Okay. Okay. Final F divides x power q power d minus x. There error minus x. How to see this? F divides. Okay. F is the monic irreducible polynomial over final field F. Order is Q. E. That construct is also a final field with cardinality Q power D. D is degree of F. E is the plane. It's the plane chain. It's the plane chain field of this polynomial. Okay, alpha is the root of the F. F is an irreducible polynomial. Okay. Alpha is the root of the case. Alpha is a element of E, of the final field E. And alpha field E is the plenty field of the polynomial Alpha is the zero of this polynomial. So alpha is the zero of f and zero of polynomial x power q power g minus x. Since alpha is irreducible, alpha is the factor of this polynomial, because f is the because oh, the no, the divisibility is a consequence of f is the irreducible polynomial. Okay. We continues. E is a plenty field of x power q power g minus x. For that, divisibility relations is equivalent to this theorem. Okay. And this divisibility relations is a consequence of this arithmetic result. This GCD of xn minus 1 x m minus 1 égale x GCD n m minus 1. Therefore, x n minus 1 divides x n minus 1 means that n divides m. If p if a finite field order q d is contained in finite field order q minus m. You recall that this finite field is the Planting field of q power g minus x. This field is the Planting field of x power q power m minus x. Any root of this polynomial is also root of this polynomial. This means this polynomial divide this polynomial. I apply this equivalence. We have d divides m. Okay. Donc, this theorem give this example. We recall that f is the irreducible polynomial. If irreducible polynomial divides x power q power m minus 1, this means that the degree of f divides degree of m divides m. Okay. Um, we the primitive element of the final field allows us to define two maps. First map is the discrete exponential in basis alpha, and second map is the discrete algorithm in base alpha. This map is bijective and reciprocal. This map is bijective. First map is easy to compute, and second map is the hard to compute. Is the hard to compute. This problem is called in cryptography discrete logarithmic problem. Is highly to obtain a discrete logarithm of element in the basis alpha, where the cardinality of the final phase is the very huge. Okay. We can prove that you can prove that for any prime number and any positive integer, we can the monic polynomial exists. Okay, you go to the board. You go to the board to explain that. Explain that okay. Okay. Q in this D is the set of monic polynomial, is the monic irreducible polynomial over finite field of monic irreducible polynomial. Over f of discrete D. Okay, we take we have this result. If f is the element, if f is the element, then f defines, if and only if degree of f divides m. Okay. We can factorize. We can factorize polynomial by d. Use this equivalence. F in this set. Okay, you use a degree. Degree of this polynomial is q power m. Degree is this product is sum d divides m, and any polynomial in this set has degree d. So that the degree of this polynomial between brackets equal d times cardinality of this set. Okay, I use Mobius inversions. Mobius inversions is the arithmetical result. Mobius inversion alone to have this. Yes, express number of the polynomial, number of the monic EG polynomial over finite f of degree d is equal sum d divides m nu of d power over m q power d. Nu is the function. Nu is the Mobius function. Nu is the Mobius function. Nu is the Mobius function. Okay. So, then we obtain this result. Nu is the Mobius function. Okay. Mobius function, Mobius function. Mobius function. When you take Mobius function is the map to Z finite. The factorization into prima number. Mobius function equals 0 if they exist alpha e greater than 2 equal minus 1 power k if alpha 1 is okay. Okay. Place can place can dot head you.
M5, destination place Chipier.
Okay, donc let us continue. Okay, Mobius function defines by this. For example, Mobius function of 12 is
Prochaine station, next stop, Rivaux.
4 is this 4 is the square. Mobius function is 0. Mobius function is 6. 6 is 2 times 3. There are no square in these products. You use seconds time equal minus 1 power 2. Okay. Okay. This equality 7 allows to see that the number of the monic polynomial over finite field order Q of degree D is different of 0. Other words, there exists the monic polynomial, there existed a monic irreducible polynomial over any finite field of any degree. This is important to start this theorem. The finite field of any order exists and indexless up to isomorphism. Existence is the consequence of it, and unicity is the consequence that this isomorphism for any monic irreducible polynomial over finite field, we have this isomorphism. So that is the second. We denote the finite field of order Q, FQ, simple FQ. To construct a finite field FQ, we need to determine a irreducible polynomial over irreducible polynomial over finite Q. Okay. What is the minimal polynomial of the element beta over Q? The minimal polynomial of beta over Q is the monic generator of integrals care of the map if beta is the valuation of any polynomial over f in beta. This injers is maximal. A ring, this ring that is in this ring, any maximal injers is generated by irreducible polynomial. A monic irreducible polynomial f over fq is primitive if there exists an element alpha of fq such that f is the irreducible polynomial of alpha. Okay, the primitive polynomial is important to construct the construct of group of inversible, the group of inversible element. The primitive polynomial is important to construct the unit group of the finite field. Okay. The number of the primitive polynomials is given by equality. I explain that. We know that when J is the final group, the final second group generated by alpha, J is the final group. The number of generator of J is given by phi. Phi is the Euler function. Recall that phi of k, phi of integer phi of integer is the number of integer between 1 of n such that GCD of k of n equal 1. Okay. We prove that is circle. This group is circle. They are phi of q power d minus 1 primitive element. Now, minimal polynomial of alpha over q it factorizes over q. But degree of this polynomial, which is the degree? This polynomial. Degree is a polynomial is d. I between I go to 0 to d minus 1. Any alpha power q power I is also primitive element of this group. So the number of primitive polynomial equal phi divides d. This is the number of a primitive element, and this is the number of a primitive polynomial. Okay. Polynomial basis. The polynomial basis is the n-tuple 1 alpha dash 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 alpha minus m alpha power m minus 1. Alpha is a root of a monic irreducible polynomial. In this polynomial basis, the additive perform additive is the sample. It is enough to compute the coefficient. For example, the construction of the fp power d. P is the prima number. We have the prima, the field order P is a sample to construct that. It suffices to take a prima number P. In circle, to construct fp of alpha. Alpha is equal x plus maximal integer generated by f. F is the primitive polynomial. You note that alpha power k is easy multiplications. We can have two representations. First representation is the multiplicative representation. Alpha is the primitive element. Alpha power k between 0 to p power d minus 1. Second representation is additive to represent any element of the field in the polynomial basis. For example, we take p equal 5. First polynomial is the irreducible over finite field order over f5. We have f25 by this construction f5 alpha. Alpha equal alpha square equals 2. I explained that. Okay. We want to construct F25. Okay, first I take F, monic irreducible polynomial F égale X square plus plus 3. Alpha X, so that alpha égale alpha square, alpha égale minus 3 modulo 5 equal to F5 F alpha. Polynomial basics are 1 alpha. Here, M equal to alpha square equal 3. Alpha power 3 equal alpha times alpha 2 equal alpha square equal 2. I count alpha 4. Alpha square 2 times 2 equal 4 modulo. Okay. Alpha 5. Alpha 4. Alpha 4. Alpha power 4 equal 4. Alpha 6. Alpha 5 plus alpha alpha 4 times alpha 4 square alpha times 2 8 modulo 5 equal 3 and so on. Okay. On the left, we have multiplicative representation. We see that alpha 3 equal alpha power 3 equal alpha power 11. 2 we are equal alpha 2. When to take a primitive polynomial, we can express any power of beta. We have to any element of the multiplicative group. Of the conclusion is the beta to use a primitive element to compute any element of the unit group. Okay. Okay, Galois construction, Galois extension. Galois extension, we know that field, that's we are the error. Okay. Yeah, there's some error. Field is the subfield of this if and only if T divides N. This we call that phi is a Galois extension of FQ. Galois group of this extension. Well, we note that is the circle. We note that Galois extension this. Galois group of this extension is the set of all ring automorphisms that fits any element of FQ power D. I denote that out. Okay, I denote that this. Okay. What is the degree of the Galois extensions? The degree of the Galois extension is the dimension of the vector space FQ power M over FQ power D. FQ power D. Okay, we have these Galois extensions. Degree is the dimension we know that with the dimension, a defined degree of dimension of this of FQ of this vector space over FQ power D. Okay, Galois group of these Galois extensions are circled generated by Frobenius. P is a characteristic of the finite field P. P is the P is a characteristic of this. Okay. Frobenius map the finite as when x sent to x power p. Here is a Frobenius map q equal p power n. Frobenius map r l. L is the degree. L is equal to m over q. Okay. The primitive, a primitive n rod of unity in the finite field FQM is an element beta of this field such that the order of the circle group generated by beta equal M. Okay. We have exercise. We do this. Do this exercise. Okay. The primitive F rod of unity in this final sheet. Beta is a primitive if the order of subgroup generated by beta equal M. Okay. Okay. We recall that order. We recall that this group is generated. This group is a circle. So alpha is a primitive q power m minus 1 rod of unity in this field unity. Okay. By alpha, you construct this is the unit. This is the n. This is the primitive q minus 1 rod of unity in this field. In this field, and so on. You construct. Generally, you construct the primitive nth rod of unity in this final field. N defines here. M is the multiplicative order of Q in this group. You compute some example. You write some example. We write some example. We take n equal 15, q equal 2, and where is the order of q in this group? We compute 2 square, 2 free, 2 power 4, 2 power 5, 6. Please. Okay, 6 equal 8. The order of 2, multiplication order of 2 in this ring equal 4. This is important, the second one, to compute the cyclotomic causal. Okay, we told. Okay. Okay, what is class math? Class math is the sum of all automorphisms. The sum of all automorphisms of the Galois group. Summary, D is Galois group of this extension. Class is sum is the okay. Class is the non-zero map that K of class is a epimorphism of the FQ vector space. K is isomorphic to K okay. FQ first theorem isomorphism FQ on this class. Class K of class is different of FQ or FQ. So that to prove K is different map, you use Aten lemma. Aten lemma says automorphism group of automorphism is linearly independent. Okay, K is a linear form. K is the linear form. K is a linear form. K is the linear form. K is the linear form. And use linear form to define a binary form class of these products. This binary form is non-degenerate and used to construct a class dual basis. Okay, class dual basic given by this equality. Class dual basics is the basis verify this. In basis verify this. Basics verify this. We take A polynomial basics. Okay. Okay. This alpha star is the class dual basic if we have if you have alpha I, alpha j star égale conical symbol. This is one if I equal j is 0 otherwise. Generally, we can take we take any basis alpha 0, alpha 1, alpha m1, alpha n minus 1. Alpha star is the class dual basic if we have this relation between two basics. Okay. To construct a class dual basics from a polynomial basis 1 alpha 1, we take we fill order 20, order 25. Alpha verify alpha square equal alpha plus 3. We compute alpha power 5. We use a relations alpha square equal alpha plus 3. Alpha power 3 equal alpha dot alpha square, or we use relations alpha square equal alpha plus 3 and spend and obtain alpha power 3 equal 4 alpha plus 3, and so on. We compute the power of alpha. When we finish to compute power of alpha, we use a formula of Kress of these extensions. Kress of these extensions the degree of this extension is 2. Is 2. Alpha square equal alpha plus 2. I think that is correct. Plus 3. Okay. Class Galois group of these extensions generated by sigma 5. Sigma 5 x since x power 5. Class extension of this extension equal identity plus sigma 5. This is the class extensions. Okay. Use class math is important to construct some family of code. Error corrective code, some error corrective code can be constructed by using the class map. This is the tool. This is an important tool to construct this code. To factorize x power, to factorize this polynomial is important to construct a cycle code. Cycle code is constructed to using this polynomial x power n minus 1 over fq. Cyclotomic concepts modulo n is the equivalence classes under equivalence relations, and explain this. We take a positive integers and q prima power such that GCD of n of q equal 1. N of q's are copram and defined on this set, these relations, and this set Zn is the integers, is the ring of integers modulo n. If y is equal to q power I times x for some non-negative integers. Q cyclotomic concepts modulo n is a equivalence concepts equivalence classes equivalence class with respect to these equivalence relations. So we express Q cyclotomic concepts with representative S by SQ square dash SQ MS is the cardinality of these Q cyclotomic concepts. Okay, we have the set of cyclotomic concepts form a partitions of the Zn Ambiguity is the partitions of cyclotomic concepts. S is the representative of these cyclotomic concepts. Okay. Donc, when you use cardinality, N is the sum of cardinality of any concepts. Okay, that is exponent. When we have any Q-cyclotomic concept modulo N, we can able factorize n minus x minus n, x power n minus 1 over or in this ring. Q is the cardinality of the field, n is the degree of this polynomial. Okay. Well, for example, we take Q equal 2 and N equal 15. First, we multiply Q, multiply by Q repeatedly. We obtain 2. We obtain 1, 2, 4, 8, 16. 16 equal 1 modulo 15. Class cyclotomic of representative 1 is the set 2. The set 2 is set 2. 2 is set 2. C1 the class 2 cyclotomic concepts modulo 15 equal set of 2 of 1, 2, 4, 8, and so on. We compute the class cyclotomic of representative 5, 3, and 0. We know that the class cyclotomic of representative 0 is the singleton. Okay, is the singleton. Donc, in this case, we have 1, 2, 3, 1, 2, 3, 4, 5. We have 5 class cyclotomic. We have 5 class cyclotomic. Well, if we have the time, we use SessionMath to compute this class cyclotomic. Okay. Okay. Which is the relationships between a Q-cyclotomic concepts and factorize and irreducible factorize of polynomial x power n minus 1. That is our questions. Explain that the explication of this, the answer of this question, we answer of this question is given by this, Okay, if you take a primitive polynomial over fq of degree n, we have alpha is the root of the polynomial. Okay, we explain that to the board. Okay, we take the primitive polynomial over FQ of degree M. Then alpha equal x plus is a root of f. The root of f is the root of f. How? Alpha is the element of these extensions. Of these extensions. Of these extensions, f alpha is the principal index. A principal index is the zero of this ring. Donc, f of alpha is equal 0. Okay, we clarify this. J Galois automorphism group of this extension of these extensions. The degree of these extensions equal the order of this group. Order of this group equal m. So f express us this product E go to 0, E go to 0, 2, go to 0 to m minus 1, m minus 1, s plus alpha power q I. This simple x sigma q is the power of the Frobenius map E alpha. Okay. We continues. Okay. You put some degree of Galois group is m. Okay. The root of the irreducible polynomials what is the same? The root of the same irreducible polynomial are conjugate. The root of the polynomial are alpha, sigma alpha, sigma dash dash dash, sigma alpha minus sigma sigma power n minus 1 alpha. This alpha power 1 power q, alpha q power, we will take the exponent. We have alpha, we have 1 q, q this set is the cyclotomic. Cyclotome is the q cyclotomic of representative 1. Of q cyclotomic representative 1. Okay. F is, we can write F as follows, is x alpha t. T is the element of the q cyclotomical set of representative 1. If you use the minimal polynomial, f is the minimal polynomial of alpha over q. Over q. Over q. Okay. Over q. Okay. If we can take this idea, the minimal polynomial okay, we return to place. Dear Professor, where will we obtain? No problem. No problem. If the end of the call and send all slide. I send all slide. I give you I give you my email. You are saying the slide. No problem. Okay. Of course. Of course. Yeah, no problem. Okay. It's finished. Okay, please, je pense que je voudrais comme. Okay. To finish, 5 minutes. If the minimal polynomials, we can use the cyclotomical set to determine the minimal polynomials. This example give the angels. Okay. Finally, to factorize this polynomial, Firstly, we determine all Q-cytomic concepts modulo n. Secondly, I compute the order de Q modulo M1. And finally, to find the primitive element and the final omega primitive F rod of unity and factorize x power n minus 1 into a polynomial over fq. Okay, please, we can result this. To factorize over this polynomial, we write this n1 is co-prime to Q. Okay. This first and second to factorize T go to 1 and R over Q omega ST. Okay. This polynomial compute omega ST omega ST place omega ST okay, omega ST okay, this okay, this is equality. Okay, omega ST. Okay, it's good. Okay, omega ST. Oui. Yes. Okay. T. Well, T. I is okay. To factorize this polynomial, to firstly to write exponent os polars and secondly to factorize place power q is to factorize x power n minus s power n1 minus 1 into irreducible polynomial. omega S, omega S, omega S, omega S, omega S, omega S is the power is omega. Omega is the primitive F word of the unity in this field. Okay. 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 The second lecture to generalize the Galois field to Galois ring. The Galois ring is a natural generalization to Galois field. The factorization of x power n minus 1 is very important, is the circle of this school. And so on, we tell you, everyone, very thank a lot for your kind attention. Thank you. Okay, je vais give. Okay, right. I finish. Please, I want to send my email to this. Oh, yes. Gmail. Gmail.
Welcome.
Thank you. Thank you.